Welcome to the course of thermodynamics of fluid phase equilibria, and in these few first lectures we are going to review the engineering thermodynamics to build the base for dealing with the more complex thermodynamics for fluid mixtures. Okay. So, I will start first with the objectives of few lectures. So, we will be covering basic concepts and definition, system and surrounding, property of a system, state and equilibrium. I will define intensive and extensive properties of a system. So, let me start first with the dimensions and units. So, any physical quantity which we are interested in thermodynamics will have to have a certain dimensions which are defined in terms of units, and these are associated with certain magnitude. Some are primary dimensions and some are which we call it fundamental dimensions, and others are the derived dimensions. The primary dimensions are mass, length, time and temperature, and the secondary dimensions or derived dimensions are the one which depends on the primary dimensions, such as velocity, energy and volume. Okay. Now, there are many ways to represent these dimensions, and that is what we call it systems. One example is standard international or international standard systems, which we call it SI, metric SI systems, which is a simple and logical system based on decimal relationship between various units. The examples of SI units for example, length is meter. So, length is meter, for mass it is kilogram, for time is seconds, then for temperature it is Kelvin and so forth. In addition to this fundamental 7 fundamental dimensions which is listed here, we also make use of standard prefixes. Okay. For example, 10 to the power 12 Pascal would be terapascal, 10 to the power 3 Kelvin would be kilokelvin. Usually we know that is a kilogram, for example, that will be 1000 gram and so forth. Okay. So, of course, we make use of the prefix which we commonly see in our calculations. Now, in addition to this, for given equations which we often deal with thermodynamics, we must make sure there is a dimensional homogeneity. What does it mean? It means, for example, if you have an equation A x plus b is equal to c, okay, it means that these terms will have the same dimensions, okay, and this has to be ensured. Now, whenever we deal with thermodynamics, we often are interested in certain systems, okay, certain particular devices where we are interested to understand what is the typical changes in the energy of a system. So, we must go through formal definition of the system, surrounding and the boundary. A system is a quantity of matter or region in space chosen for study, and surrounding is whatever is outside the system, that is mass or region outside the system, and this is separated by boundary, does not have any specific volume there, does not have any volume. So, thus the boundary could be a real or imaginary surface. It usually is fixed, but it could be also movable depending on the system which we are interested in. Okay. In addition to that, it could be adiabatic or it could be diathermal. Okay. So, let me just go through now specific examples, the closed system and open system. So, what are the closed system? Closed system is where basically no mass can leave or enter, but energy can cross the boundary, okay, in the form of work or heat, which we are going to define more specifically later. In addition to that, the volume may change because the boundary need not be fixed. So, this is an example of a moving boundary cylinder piston system, where the piston will move depending on if there is a specific if there is a heat supply to the system, and thus the volume can change. Okay. So, volume may change, but no mass can enter or leave, that is basically the closed system. If you do not allow the energy to get in or get out, it will become an isolated system. Okay. Now, what are the open systems? Now, open systems are often seen in many devices. Okay. The examples are widespread, pump, compressor and so forth. Now, in this case what happens is the mass energy both can cross the boundary. Okay. So, both mass and energy can cross the boundary of the open system, which often we make use of the definition or the synonymous synonymously we also define it as control volume. So when somebody says control volume, it essentially means also open system. So when this is an example of a real boundary where the boundary is a fix, okay, it's not moving. So and this is a combination of actually the real boundary and imaginary boundary where the boundary is fixed and the mass can flow in and out. Okay, energy of course can also flow in and out. Now this is an example where one boundary is movable, the others are fixed. Okay, and this is an example where the boundary is completely fixed, okay, for the control volume. This is an example of a water heater. Okay. So a control volume can be any arbitrary region which basically would help in analyzing the system. Okay. It need not be a specific way to define a control volume. It is basically entirely dependent on yourself. In order to solve a certain problem, you have to define the control volume more thoughtfully. Now there are many examples in nature of what we do in regular life. For example, this is coffee. This is an example of open system. The next is of course a can, closed system. When it is closed, it is not used, it will be a closed system. And then you have this kind of thermos which is usually used in order to maintain the temperature of the whatever the fluid we put there, and this essentially is an example of isolated system. Okay. All right. Now what we are interested in when we deal with the system, we are essentially interested in the property of a system. Okay, and the property may change depending on the condition of the system. So conditions such as temperature and pressure. An example is basically a container containing nitrogen and hydrogen where the reaction is occurring forming ammonia, and this will depend on the temperature and pressure, or in other words the gas mixture depends on the temperature and pressure, and thus it is important that we must understand the property of a material as we change the variables. Okay. So how do we define a property? Okay, or in other words, what are the essential features of a property? So property should have a definite value, okay, when a system is in a particular state. So in other words, it does not depend on how the system has arrived to a certain state. Okay, it will have once you arrive at a certain state, it will have a specific property. So the value of the property should be determinable irrespective of how the system is brought to the particular state. In other words, the property is independent of path. Okay. So if Z is a property, okay, and usually we are interested in the difference in the property from initial state to the final state, then dz should be an exact differential, okay, leading to this integral. In other words, the property or thermodynamic property is a point function because it does not depend on any specific path. Okay. Now what are the examples of the property? The properties such as pressure, temperature, volume. Okay, these are the properties. Okay. Now properties can be extensive, which depends on the mass, and okay, or it can be intensive. So the intensive property, which is independent of mass, for example, is temperature, pressure, and density. So if you consider system having a mass V, volume, temperature, pressure, and density, and you divide by 2, or you divide this into 2 halves, then mass will get divided by half, volume will get divided by half, but this will not, and this is the reason that it is basically an intensive property. Okay, whereas the extensive property are those which depends on the extent of the system, such as mass, volume, total momentum. You can also extract a specific property out of extensive property by dividing it by mass, such as specific volume. So let me now define state and equilibrium. A state is nothing but when the system arrived at a condition where nothing undergoes any change. So and that is what we call it a state. So a system is not undergoing any change, and at this condition one can measure all the properties describing the condition. So for example, this is one state and this is state 2 for the same gas, but a different volume. Okay, and what we are interested here is the property, and usually the property in such a case will be uniform. That is what we assume when we define a state, and when we fix the parameters such as temperature, volume, a specific property comes out of it. Now in addition to state, let me now define equilibrium. So equilibrium is nothing but, is obvious, is when there is no state of driving force, or there is no driving force, and the state of balance. That means there is no unbalanced potential within the system. So, for example, this is an example of a closed system before equilibration, and this is an example of closed system before the equilibration, and this equilibration we call it thermal equilibration, because here all the points are fixed, or rather are not changing. Okay. An isolated system at equilibrium, that means it is not interacting with the surrounding, eventually it means that it undergoes no change, okay, because it is isolated, there is no interaction with the surrounding, and hence all the properties remain same, okay, as long as it is under isolation. So, in this course in general thermodynamics, particularly equilibrium thermodynamics, we are interested to understand a system at equilibrium. So, when we talk about equilibrium or thermodynamic equilibrium, there are three important criteria. One is thermal equilibrium, where there is no temperature gradient, and in other words no heat flow. And second is mechanical equilibrium, that means there is no force gradient, or in general there is no change in the pressure, okay, within the system. But of course, the pressure can change along here, along the vertical direction, but the pressure will remain same along the horizontal, and in other words the forces are balanced in order to achieve a mechanical equilibrium. And chemical equilibrium is if the chemical composition of the system does not change with time, that is there is no chemical reaction. Okay. So, that means all the compositions here and here will be constant, and there is no mass transfer from this point to this point, okay. That will indicate a chemical equilibrium. And the phase equilibria, which we are going to deal with more intensely in the later part of this course, is a system involving two phases, alpha and beta, okay, and the mass of each phase reaches an equilibrium level and stays there. So, that means effectively there is no mass change from this phase to this phase, okay, it remains as a constant, okay, effective rate of mass will be exchange will be 0. Okay, but of course, phase equilibria there is more formal definition which we are going to deal with little later. Okay. Now, in order to define the system, we call or the property, then there will be certain property which will be required, and now that will depend on whether this system is a single phase or two phase or many phases. Okay. But let me just define a formal definition of something called state postulate, which is nothing but a state of a simple compressible system is completely specified by two independent intensive properties, okay. So, which could be a temperature or pressure, okay. And what is a simple compressible systems, such as this example of nitrogen? If a system involves no electrical, magnetic, gravitational motion and the surface tension effect, then the system is called simple compressible system. So, in this case we used two variables, intensive variables, to define the state of the system, okay. But as I said, now it depends on whether the system is in a single phase and two phase and so forth. For example, in this case the system is in one phase and hence we needed two, but if it is a saturated vapor or liquid, we just need one variable, or it could be temperature or pressure. Other variables are fixed for a single component system. In a formal way to define the number of variables needed to define a system is given by Gibbs phase rule, okay. So, this is the number of degree of freedom which is required to define system. This is C is a component, number of component of the system, P is number of phases, and plus 2. So, we will be discussing this part more in detail later in the course. Okay. Now, let me also define process. A process is any change from one equilibrium state to another state. So, this is state 1 and this is state 2, and this property A versus property B plot is called process diagram, okay. And from state to A, state 1 to state 2, there is a change, okay, and this change is drawn by this shown on by this green line. This is called process path. We could show this green line for an equilibrium or quasi static or quasi equilibrium, that means very slow process, okay. For very fast process we cannot show it on the process diagram, such a change, okay. So, this is a path, okay. As I said, quasi static and quasi equilibrium process are the process which are very slow, such that the system remains infinitesimally close to an equilibrium state at all time. So, very fast compressible compression would be a non-quasi equilibrium process, and we cannot draw such a process on a process diagram. Okay. Now, there is a reason for making an assumption like this, because by considering quasi static equilibrium process, we can idealize processes and analyze devices and find out maximum work to be done or the minimum work required, for example, by a pump in order to operate, or similarly work produced in devices such as turbine, how much maximum work can be extracted from there. Okay, so, this is all based on the quasi equilibrium concepts. So, as I said, this is a process diagram. Example is a PV diagram. Okay, property A and property B is P and V, and in the compression it is shown that it is slow compression, we can draw it in this form. Okay. Now, in addition to process diagram and process path, there are various different processes that depends on the conditions which we are imposing. Isothermal process is the one where the temperature is fixed. Okay. Isobaric where the pressure is fixed, isochoric where the volume is fixed, particularly specific volume, or where the volume is fixed. And the cycle is a process during which the initial and final states are identical. Okay. In addition to these processes, we have conditions where the flow is being considered, where many example of such processes, these are turbine, pump, boilers, condenser and so forth. Now, for the case of such a system, when the process itself has reached a steady flow, which means there is no change in the time of the property, okay, this will be called like steady flow process. So, okay, so the steady flow process is a process during which a fluid flows through a control volume steadily. Now, in addition to that, there is something called uniform. So, uniform is no change within location. Okay. So, a steady flow process need not mean a uniform process. Okay. Where steady means, for example, you have a time at 1 where the temperature distribution on this control volume is 300, is this given here, whether effectively there is average temperature, but it can change within this control volume, but at 3 p.m. there is no change in the temperature, and thus it has reached a steady flow process. In other words, in the control volume the mass or energy will remain constant, in general property will remain constant, but it can vary within the control volume, okay, but it will not vary with time. Okay, so with this basic definition we will end this particular lecture, and we will see again next time. We will continue this review process for another few lectures. See you next time.